Assalamualaikum warahmatullahi wabarakatuh, and a very good day to Rahib. We are from Group G. We will be presenting our group project which entitled New Chemical Inhibitors for Gas Hydrate Prevention Latest Development in Kinetic and Thermodynamic Inhibitors. Our group consists of 5 people, which is Natasha Azira, Muhammad Nazimuddin, David Darren, me myself, Muhammad Arif Aiman, and also Muhammad Arif Akmal. What are gas hydrates? Gas hydrate is an ice-like crystalline solids where gas molecules, which is mainly methane, are trapped in a lattice of water molecules. How does the gas hydrate form? These hydrates will be formed under low temperature and high pressure conditions. The cause of this hydrate form is by the cooling of transported fluids below the hydrate stability temperature. Now, let's discuss on the impact of these gas hydrates. This impact is really significant on the flow assurance, where the hydrates can cause severe blockages, increase pressure drops, and also potentially damage the equipment. All of this impact, if we not manage it correctly, they can lead to complete shutdowns of production systems. That's why hydrate prevention is a major part of flow assurance strategies in the oil and gas industry. To prevent hydrate formation, there are 3 main conventional prevention methods, which are depressurization, thermal management, and also chemical inhibitors. As for depressurization, it will reduces the pipeline pressure to move the system out of the hydrate stability zone, which effective during the shutdown or remediation. As for thermal management, it will be used by direct heating or thermal insulation to keep the fluids above a hydrate formation temperature. But this method is quite costly and also quite challenging in deep water operations. As for inhibitors, there are 3 types of chemical inhibitors, which is firstly is thermodynamic inhibitors. As example, the methanol or monoethylene glycol, or MEG in short. This require in high volume, which is up to 50%. And these inhibitors will be increase the more job, lot of works in logistics and also the regeneration needs. The second inhibitors is the kinetic hydrate inhibitors, where it will use synthetic polymers that will delay the hydrate nucleation. It effective at lower dosages, however, it is limited in subcooling range. The last but not least is anti-agglomerants, which is a surfactant-based inhibitors, where it keeps small hydrate particles suspended in the flow. It usually used in oil-dominated systems with water cut.
Now, let's take a look at thermodynamic hydrate inhibitor, or THI. The primary purpose of this THI is to prevent hydrate formation by shifting the hydrate equilibrium. This means they make it harder for hydrate to form and requiring lower temperature or higher pressure for stability. 2 of the most common THI used in the field are methanol and glycol. Methanol is typically used in batch injection, but it has high vapor loss, which means it can easily evaporate and pose safety concern. It also has high viscosity at cryogenic temperature around -40 degrees Celsius, which makes separation during regeneration more difficult. Glycol is preferred for continuous injection system. It has lower vapor loss and a lower viscosity at cryogenic condition, making separation and recovery more efficient. On the right, you can see a figure, the illustration how a THI shifts the hydrate phase boundary. By adding THI, they move to the left, requiring colder temperature and higher pressure, which help keep the system hydrate free. Next, in this slide, we're looking at how limitation in the mechanism of thermodynamic hydrate inhibition have directly driven innovation in a new development. First, THI work by altering the chemical potential of water to shift the hydrate equilibrium curve. Because of this, they require very high concentration, often between 10 to 50% of the water phase, which add to cost and handling of low dosage THI or LDHI, which can achieve similar inhibition with much lower amount. Next, THI are not selective and they often interfere with other additives used in flow assurance, such as corrosive and scale inhibitor. The response has been the creation of multifunctional THI that are compatible with other chemicals in the system. In deep water operation, when temperatures are much lower and pressure higher, conventional THI often struggle to perform. This pushed the development of formulation design specifically for extreme environment, improving reliability and additionally, since THI are fully miscible with water, their recovery and regeneration typically require energy-intensive process. To address this, newer THI are being designed with bio-based or phase-separable properties or simplified reuse. Additionally, there are health, safety, and environment concerns, especially with traditional options like methanol due to toxicity and flammability. This has encouraged the move toward greener, biodegradable THI that are safer for handling and better for the environment. THI are fully miscible with water, their recovery and regeneration typically require energy-intensive process. To address this, newer THI are being designed with bio-based and phase-separate properties to simplify reuse. Overall, this slide highlights the natural evolution of THI technology, where mechanism-driven challenges have led to meaningful scientific and practical improvement.
Hello, my name is Muhammad Nazimuddin, and now I will continue this presentation with slide kinetic hydrate inhibitor KHI, which is the basic one. For the function, we need to know that this KHI delay the nucleation growth of gas hydrate rather than we are altering equilibrium condition. The KHI act as a low dosage hydrate inhibitor, which is LDHI. For chemical nature, KHI is typically a water-soluble polymer such as polypyrrolidine and PVCap. In some cases, there are some copolymer which is tailored to interact with hydrate crystal surfaces. For dosage of advantages, it requires much lower concentration to 0.1 to 1 weight percentage compared to the thermodynamic hydrate inhibitor THI like methanol or MEG, which is at 20 to 60 weight percentage. For it also a cost effectiveness in deep water and the subsea system. For operating condition, it's most effective under the moderate subcooling, and it also the performance will decrease with the extreme pressure drop or temperature drop condition or long residence times. For the limitation, we cannot dissolve it with existing hydrate. It also sensitive to the salinity, temperature, and the flow condition. The KHI also need to combine with anti-agglomerants, which is AH, in all dominated system. Hello, next we move to the latest development in kinetic hydrate inhibitor KHI. There is 4 key points that we need to know, which is first is advanced synthetic polymer, bio-inspired and biodegradable KHI, high salinity and deep water performance, and the field application and testing. For the first point, which is the advanced synthetic polymer, we need to know that there is new polymer formulation show wider thermal stability, effective in lower temperature and higher pressure, and it also enhance resistance to the degradation in harsh field condition. For next point, which is bio-inspired biodegradable KHI, we need to improve the development of environmentally friendly of KHI for natural or renewable sources. We also need to design for low toxicity and rapid biodegradation that meet the stricter offshore regulation, which is OSPA. For the high salinity and deep water performance, we need to know that we need to improve the salt-tolerant polymer to ensure the stable performance in high total dissolved solid, which is TDS, that it also tailored for the deep water flow line with long residence times and low seabed temperature. And the last point is field application for testing, which is we need to do some trial or some tests to show a promising hydrate inhibition with that will reduce the chemical footprint, and also we need to do some new KHI compatible with the multi-phase system and anti-agglomerate, which is AA. That's all from me. That I will pass to the next presenter.
So good evening everyone, my name is Divendra. Now let's compare the performance of thermodynamic hydrate inhibitors or THIs with kinetic hydrate inhibitors KHIs based on key performance criteria. First, in terms of dosage, THIs like methanol and MEG typically require high injection rates up to 15% by weight of the water phase. In contrast, KHIs only need about 0.1 to 1% making them much more efficient. In terms of how they work, THI shift the hydrate equilibrium, preventing hydrate formation entirely. KHI, on the other hand, don't change the thermodynamic condition, but they delay hydrate nucleation and growth, giving us more operating flexibility. THI are effective across a wide temperature and pressure range, making them very dependable, but they also come with higher environmental impact, especially with larger scale methanol use. KHI are much cleaner, especially when biodegradable formulations are used. When it's come to regeneration, glycol-based THI can be recovered and reused, while KHI are generally single-use and non-recoverable. Finally, from a cost perspective, THI are more expensive overall due to high volume and loss. KHI may have a higher per unit cost, but their low dosage requirement often make them more economical for long-term use. So overall, each inhibitor type has strengths and trade-offs, and choosing the right one depends heavily on the specific operating environment. So, despite these advances, applying hydrate inhibitors in the field still comes with several challenges. Firstly, field performance can vary. KHI that work well in the lab may not perform consistently in real pipeline conditions, especially in multi-phase or turbulent flows. Secondly, compatibility in major concern. These inhibitors may interact negatively with other chemicals in the system like corrosion or scale inhibitors, which could reduce their effectiveness or cause emulsions. Operationally, precise dosing is critical, especially for KHI which have a narrow window of effectiveness. This demands advanced injection and control system. So on the top of that, environmental regulations are becoming stricter, particularly for offshore and Arctic operation. This limits the use of traditional THI like methanol and drives the need for greener solution. Lastly, the cost benefit question. While KHI are low dosage, some of the newer formulation can be expensive to produce, so operator must evaluate whether the performance gains justify the cost, especially in larger scale or long duration projects. Addressing these challenges is essential for fully unlocking the potential of next generation hydrate inhibitors. Thank you.
Now, I will explain the future outlook for gas hydrate preventions. One of the main direction in research today is focused on green chemistry and sustainability. So this means creating inhibitors that are biodegradable and cause less harm to the environment right now. Many companies still use traditional inhibitors like methanol or MEG, which are classified as thermodynamic hydrate inhibitors, which is THIS. These chemicals are effective, but they require large amounts and have a negative environment impact. That's why scientists are now developing new eco-friendly alternatives that can meet stricter environmental regulations. Another promising area is nanotechnology and hybrid inhibitor systems. Researchers are working on nanomaterials that can improve how well the inhibitors perform. There are also new hybrid systems being developed that combine the advantage of kinetic hydrate inhibitors, which is KHIS and THIS. This is especially useful in complex conditions such as deep water pipelines, where temperature and pressure changes are more difficult to control. Technology is also playing a big role in hydrate preventions. With real-time monitoring and digital tools, we can now predict when hydrates are likely to form. AI and flow assurance models analyze pipeline data and help operators adjust chemical dosing on the spot. So this kind of smart dosing based on sensor feedback improve efficiency and save costs by using the right amount of chemicals at the right time. Lastly, the overall direction for the future is clear. We are moving towards low dosage, high efficiency inhibitors that are safer and more environmentally friendly. So these solutions are also being designed to perform well in challenging environments such as high salinity zones and deep water fields. So this innovation will help make gas production safer, cleaner and more reliable. So in conclusions, the future of hydrate prevention is very promising, which is driven by sustainability, smart technology and advanced chemical solutions. To conclude my presentations, I would like to summarize the key points we have discussed. So we have looked at the recent advancement in two main types of hydrate inhibitors, which is thermodynamic hydrate inhibitors, which is THIS, and kinetic hydrate inhibitors. which is KHIS. So THIS, like methanol and MEG, work by shifting the temperature and pressure conditions to prevent hydrate formations. However, they require high dosage and can be harmful to the environment. Today, new THIS are being developed that use lower dosage, less toxic, and can even be recycled. KHIS, on the other hand, work differently. They are made from water-soluble polymers and delay of the formation of hydrated crystals. Recent innovation have made KHIS more biodegradable, effective over a wider temperature range, and more compatible with extreme field conditions. So this makes a better fit for deep water and high salinity environment. Innovation in this field is very important. Without proper hydrate management, hydrates can block pipelines, causing shutdowns, equipment damage, and safety issues. With the development of improved THIS and KHIS, we can ensure safe, efficient, and continuous flow of oil and gas. So, these innovations also help reduce environmental penalties and support long-term sustainability goals. So, finally, I will like to end with this thought. The future of hydrate prevention lies in smart, sustainable, and synergistic inhibitor systems. This means that we are not only focused on stopping hydrate formations, but also doing it in a way that is smarter, cleaner, and more cost-effective. That's all from me. Thank you.